Hello everyone, welcome to the second session of Embedded Systems course. In last session, we got a brief overview of embedded systems and its types, its application domains, its features and characteristics, its various types based on certain parameters and the design cycle of a general embedded system. In this session, we'll go over various design approaches of how an embedded system is designed. Then we'll go over basic component and an important component of embedded system, which is a processor, and what is the difference between a microprocessor and a microcontroller. Then we'll see how microprocessors are classified based on the instruction set. So let's start. So embedded systems in general are designed using two approaches. One is the FPGA approach and the other is the ASIC approach, right? So what is FPGA? FPGA is field programmable gate array, right? So as the name suggests, this design approach is programmable. Okay, the design is you can program and reprogram, so, and it is used for general use, right? It will not be designed only for one specific set of functions. Like the same logic or the same design, you can configure it as a GPU, or the same the logic you can configure it as a microprocessor as well, right? So what it contains certain programmable interconnects, and it has certain configurable logic blocks, right? So if you come to the diagram, right, so if you see, so these are your configurable logic blocks, right? And then these are the interconnects, right, which connects these configurable logic blocks, right, towards each other. And these are the input output blocks where you can connect your peripherals. We'll see this when we have different FPGA development boards. We'll see this in the next slide, right? So, and how these these programmable logic blocks are connected to each other. They are connected through some VSDL languages. There are certain design languages where you can configure these logic blocks as per the required function, right? So this is the first approach, which is known as field programmable gate array. Array, because if you see, this is an array of configurable logic blocks, right? So that is why this is called in this way, right? So if you see, we have basically two broad vendors for FPGA development boards. One is from from Xilinx, right? And so Xilinx was currently acquired by AMD, and then we have Altera, right, which is from Intel, right? So if you see, you will have certain these input output blocks on the borders, right? And these are the peripherals, the uh, LEDs. You have this 8 cross 8 and all these LEDs there. And then this part, right, this part is the basic chip, the important chip, or the main logic board, which manipulates all the functions and all, right? And similarly, you have other ports, input output ports and all that, right? And similarly, you will see similarly from this other FPGA development board. So this is the main chip from Altera, and then you will have certain switches. So these are the switches, right? And then again you have these uh, 8 cross 8 LCDs, LEDs, all these are there, right? Then you have these ports where you can connect wires and all, right? So this is a basic development board which you can configure, right? You can dump your software through external softwares, right? And you can configure it in a particular way, right? As I told you, you can build it as a microprocessor, you can make it function as a GPU and all that. So that configurability is there, right? So now the second design approach to build an embedded system is your ASIC approach, right? So what is ASIC? ASIC is application specific integrated circuits, right? So we saw that the FPGA was programmable, right? But this is specific to certain functions or certain outputs. So this is not programmable, right? It is designed for one specific application, right, and does not allow you to reprogram or modify it after it is produced, right? So these are not produced for general purpose, and as per certain specifications or certain requirements, these are produced. So basic examples of ASICs, right, are your mobile chipsets, right? The Exynos from Samsung or the Snapdragon from Qualcomm. All these are very common examples of ASICs. Not only these, like these are very big chipsets, but you have, you have your ESP32, which is a Wi-Fi module, right? This also has a processor and certain memory, and it is a Wi-Fi module. So this also is a ASIC, which is designed for basically the Wi-Fi connections and all that, right? So we'll see this interfacing with Arduino as well in our upcoming sessions. Okay. So this was the second approach. Now, based on the design or how much it is customizable, right? These ASICs are classified into fully custom designs ASICs or semi custom design ASICs, right? So what are fully custom design ASICs? So ultimately at the gate level, right? So any logic ultimately is designed using certain gates, right? And or not, and all these basic gates. So there the transistors and the logic can be designed as per the specific request of the customer, right? So that is called fully, fully custom design ASIC. Then in semi custom design ASIC, what happens? There are two approaches, right? So there are standard cells. So these are pre-designed, pre-fixed layout library components. Standard cell libraries are there in the design, which you can configure, or some certain version blocks which you can, customize to perform certain specific functions. But the number of library components or the type of these standard cell libraries will be fixed. And then you have a gate array. So what will happen in gate array? So in gate array you will have silicon layers, and where you can adjust these silicon layers via certain transistor interconnections. So the layers will be fixed. You cannot modify the layers, but you can certainly configure the layers in such a way that these perform certain uh, certain required output, right? But what is the basic difference is that this can be configured, it is like pre-manufacturing. You can do this pre-manufacturing, you can configure this, but this is only in the manufacturing stage. So this is one difference between the semi custom design ASIC, and of course you will have one fully custom design ASIC. So these transistors and logic can be designed as per the specific request of the customer, right? Now, there are certain differences between FPGA and ASIC, because both are certain design approaches which is followed in certain conditions, and sometimes it's not followed. So how do we decide when to follow which design approach, right? So it's very important to know this. So when the time, right, to give the product to the customer is very less, right? So FPGA designs usually take less time. Why? Because their circuitries are much more configurable, right? The design cycle, the design steps are lesser, and that is why FPGA designs take less time as compared to ASICs, right? The design flow in ASICs have certain more steps. For example, the DFT is designed for testability, insertions, and all those checks are introduced in much more, and even the testing cycles and all are larger as compared to these FPGA designs, right? Now also on the speed or the frequency, right? So ASICs, of course, ASICs are faster than field programmable gate arrays, right? Because they are certain, the circuitry the circuitry here in ASICs can be scaled. The frequencies can be scaled to very high gigahertz, so these are scaled can be the components can be scaled to higher frequencies to function, because based on certain function, because you have only just one function to perform, so you can scale it before production, and therefore they are faster, right? Or of course, now cost. So when you produce in large numbers, right, so then ASICs of course are lesser cost, but for small applications, right, FPGAs come out to be more cost effective, right? But as I said, ASIC products are cheaper when you try to make the complex designs and large, right? larger number of products you have to ship, then ASIC designs are cheaper. Also, one thing, but one demerit is that the design tools, right? Because there is so much design steps involved and there is so much of testing, the uh, ASIC comes out to be a more costlier affair. Okay, so that is one thing. Now, what about size and area, right? So, of course, since FPGAs are expected to produce more than one function, right? They are programmable to give more than one desired outputs or desired product designs, right? So FPGAs are in general larger designs than correspond because they have larger circuitry, right? Some circuitries may not be used, but it needs to be there beforehand so that you can use that for certain other outputs, right? Now, what about power, right? Power is always an important parameter. So FPGA designs, right, consume more power than ASIC designs, of course, because again, or because of more circuitry, some may not be used, but still that will be there. And that is what it is saying, that unwanted circuitry results wastage of power. So ASICs are designed to be more power efficient, right, than FPGAs, right? Reusability, of course, FPGA is more reusable, right? What about design issues, right? So now the way of designing these ASICs and FPGA are different, right? The steps, the design steps are more in ASICs, right? So there will be lot more of design issues in ASICs, right? So therefore, since FPGA has a simpler design cycle, it has less of design issues. There is no DFT insertion, right? So DFT is your design for testability, your boundary scans, your JTAG scans, and all that, which is used for post-silicon, verification, and it is required for testability to give the chip the testability, or you can test it, right? Whether there is some manufacturing defect and all that. So those are inserted in ASIC designs, but not in FPGA. Hence, the design issues are expected to be less in FPGA as compared to ASICs, right? And of course, also one thing is that FPGAs ultimately consist of smaller, chips which are pre-verified. So already those the DFM issues, the signal integrity issues are taken care in the ASICs, and that is why FPGA are expected to have lesser issues. So we can say that though ASICs are more efficient than FPGA, of course, in terms of power and performance, because you can scale up frequencies and all that. But ASICs are not versatile, right? Because it is not reprogrammable. You cannot program and reprogram as per your different purposes. So that's the difference between these design approaches, right? Now we saw that one of the very important components of a general embedded system we saw was a processor, right? So now these processors can come in two types. Okay, so in the sense, it depends on what things are combined with our main processor, right? So we all know that a processor consists of a control unit, it has an arithmetic logical unit, and it has a register, right? So a basic processor or a CPU will contain this, right? But what about certain other small blocks or certain small other IPs in terms of your counters, your timers, your memories, and all those, right? Those are not integrated. If those are not integrated in the same chip, that is called as only microprocessor, right? And when you have peripherals, you have IO ports, you have counters, you have timers, you have RAM and ROM, right? If you see here, RAM and ROM, all these are integrated on the same design, on the same chip, right? So then it is called a microcontroller, right? So CPU with different, you can say that CPU plus different chips, right? That will be your microprocessor. Means there will be smaller other chip design, chips which will be integrated with your CPU chip, right? But there is, a single chip here, right? It's a single chip. So this is the difference between a microprocessor and a microcontroller, right? So here there are no, in microcontrollers there are no external peripherals apart from that chip, but in CPU there will be external peripherals. You will have your counters, your timer modules, all these will come on a separate chip, and you have to attach that to the microprocessor, right? So that is a difference between microprocessors and microcontrollers, right? So now microcontrollers example, right? So this course will deal basically with Arduino, right? Our focus will be on Arduino. So that is a very good example of a microcontroller, because you will have this is your microprocessor, but it will have your other modules integrated on the same board, right? It will come on the same circuit. So your timer modules and other IO ports and all these, right? So these ports and all these you will be able to connect on the same board, and timer modules, counter modules will all come in the same chip. So it's an example of a microcontroller. Now another examples are Atmel AVR microcontrollers, which come from microchip company, right? Then AVR, ATX, Mega, Atmega, all these you would have you'll use, or like this course currently deals with Arduino, but all these can be used as microcontrollers, and you can create small embedded systems, and of course larger embedded systems are also cool. These are very powerful chips actually, right? So these were the common examples of microcontrollers, and our course will deal with Arduino. Right now, this processor microprocessor, right, can based on the instruction set, right, you need to give certain instructions to these processors to perform certain outputs, right? So based on that, it can be CISC or it can be RISC, right? So risk is what? So risk is, as it says, it's a reduced instruction set computer, right? Or architecture. So there are smaller number of instructions in risk architecture, right? As compared to CISC architecture, which is this. So common examples I will give you, right? So the cross 86 architecture, right? From Intel, right? So that is a very common example of CISC architecture, and ARM architectures, right? Advanced ARM is a company, so their chips are basically RISC-based architectures, right? So as we said, first of all, the basic difference is that there will be more number of instructions in CISC, right? As compared to RISC, right? Now more number of instructions, so what will it will happen, that you will require more hardware logic, right, to implement those instructions, right? So what happens that CISC is more hardware oriented design, right, and RISC is more software oriented design. The hardware complexity is less in RISC as compared to CISC, right? So that is what the third point says. Hardware circuitry for instruction implementation, it's more hardware complex, right? High level compiler takes care of more. So the hardware is lesser complex, but the compilers or you will need to write more code, right? For same amount, for the same job or same output, you will need to write more code in a RISC, because two things, you have lesser number of instructions, so you will have to use all those instructions to produce the same output, right? We will discuss that as an example. The basic example is multiplication, right? If you have to multiply two data which is located in memory, in CISC you can do that operation, right? Memory to memory multiplication you can do that in CISC, but in RISC you will have to first load it, you have to load it into registers, and then you have to multiply, is then you have to do a product, right? So that is one, you can demerit of RISC, but of course we'll come to advantages also. So now since there are lesser number of instructions, so these RISC based instructions are single cycle, and these are multi-cycle instructions, right? CISC is multi-cycle instructions. Okay, so that is one thing. Now usage of RAM, right? In the sense, since memories wise, you will have to again reload, load from the memory into register, again store it into the memory. So there is a heavy use of RAM here, but I told you, like, you can directly multiply memory to memory data, so there is lesser usage of RAM here, right? Of course the instruction sets is small and it is less complex, right? In the sense, the modes or the operand modes, or however you do these manipulate these data, there are lesser addressing operand modes in RISC architecture, and uh, high addressing modes in CISC architecture, right? So large number of instructions, this was the very basic difference which we know, right? It may support microcode and only one layer of instructions. So yeah, so what is there is that the control unit, right? Also, one basic difference is that the control unit is hardwired here. Control unit is what? Control unit is the one which is generating all the control signals. So control unit is hardwired, and here control unit is micro programmed. You can program those control units to generate the signals in here, okay, in CISC based architectures. And of course, we addressing modes, right? So how you take the operands and how you address those, right? Memory to memory operations or memory to register operations, right? So there are many examples of those addressing modes in CISC base. Therefore the instruction set is large also, and it's more complex. But here there are few, it's fixed, and therefore the length of instructions is also fixed, and here it is variable in CISC based architecture, right? So this was the basic processor architecture based on instruction set, right? And this is a very important topic to know. And as we go forward, we'll be dealing with Arduino, which is a RISC based architecture, right? Which uses RISC based processor as its main core. So we will go ahead and see what all peripherals will interface to Arduino. So that will be coming in next sessions. Thank you.